Hello everybody, my name is Alex Matveev and I'm the head of development team of PES-StarProf pipe stress analysis software. And at this seminar I will tell you about the importance of the Bourdon effect and tell you what is the true and what is the effective axial force. Traditionally, the impact of Bourdon effect is not considered for the steel piping systems because it is not very important. However, for high pressure piping systems or for very long pipelines or for non-metallic piping systems like high density polyethylene, GRE, GRP, FRP piping systems, the Bourdon effect is very important and it should be taken into account during the pipe stress analysis. So PES-StarProf pipe stress analysis software always apply the Bourdon effect to ensure the accuracy of the results and to avoid the human mistakes. Some time ago I decided to create the poll on my LinkedIn account and I asked a question. For example, you had a pipe that is restrained between two anchors. The thermal expansion is zero and the internal pressure is high. The axial force will be compressive, tensile or zero. And the results was following. 32% of people vote for compressive force, 32% of people vote for tensile force and 25% vote for zero. So let me explain you what is the Bourdon effect, and after some time I will tell you the correct answer for this question. Imagine the cantilever pipe with the anchor on the one end and the cap on the other end. Longitudinal elongation of this pipe will be calculated using this equation. A is the cross-section area and N is the force caused by pressure on the end cap on this pipe. So the elongation due to the force acting on the end cap of this pipe will be following. You can see it on the screen. But this effect has the second part. It's pipe shortening under the internal pressure. The pipe shortening can be obtained from the Hooke's law equation and is following. You can see it on the screen. You will get this value. V is Poisson factor and SH is the hoop stress in the pipe. The pipe diameter becomes greater and the pipe is shortened because the volume before the deformation and after the deformation should be the same, and the total elongation of the pipe will be the sum of the two effects, and you can see it on the screen, this equation. It's 0.5 minus Poisson factor multiplied by hoop stress and the pipe length divided by elastic modulus. And also we can add here the thermal expansion elongation of the pipe, so the final equation will be like this. What will be the axial force, internal force in the pipe caused by internal pressure? The force that is acting on the end cap of this pipe will cause the internal tensile force that is equal to the area, cross-section area, multiplied by 0.5 by hoop stress. It is approximate equation. And the anchor load will be zero. How could it be? Let's imagine that our pipe is a balloon that has two end caps, and the pressure that is acting on the left cap and on the right cap are balanced. So the final force on the anchor will be zero. So we have two forces. One force is internal force inside the pipe cross section, and the other force is the anchor load, the load on the anchor, and it is zero in this example. Now let's check the totally restrained pipe. It is the pipe that is restrained between two anchors, absolutely rigid anchors. The pipe internal force will be caused only by the pipe shortening effect. So pipe tends to shorten, but the end anchors doesn't allow it to shorten, and the tensile force arise inside the pipe cross section. The end cap forces are applied to the anchors and totally absorbed by the anchors, so the end cap forces doesn't produce any internal force inside the pipe wall. So this is the equation for axial force, internal force in the pipe, and the restrained load, the load on the anchor, will be the internal axial force plus the end cap force, because the end cap forces are applied to the anchors, and the final equation will be like this. So the difference between two equations is that the 0.5 factor is added to the anchor load, and there is no such factor in the internal force equation. And I say again that internal force in the pipe will be tensile. Now let's check the cantilever pipe with anchor on one end and the end cap on other end, and this pipe is buried. It's underground pipe. This pipe will have three zones. The first zone is restrained zone, and it's caused by the compressive friction forces acting in the sliding zone. In this zone, the pipe behavior is restrained. It is totally restrained and doesn't move anywhere. It doesn't move in axial direction, and the internal axial force is constant. The second zone is unrestrained zone. In this zone, pipe behavior like unrestrained pipe with anchor and the cap on other end. But this zone is very small. It is just at the pipe end, and the rest of the piping is working like partially restrained zone. This is the sliding zone. In this zone, the pipe moves along its axis and works like the pipe restrained between two anchors with a little flexibility on the one end. This is partially restrained pipe. Here you can see the table with all the equations from the previous slides. Here is the unrestrained pipe equations. Its support load for unrestrained pipe is 0, but internal force is calculated using this equation. For restrained pipe, the axial force calculated using this equation, and support load is calculated using this equation with additional force from end caps, from the force on the end caps. This is the axial stresses and pipe elongation. The pipe elongation for restrained pipe will be 0. and these equations are for partial restraint pipe with a small flexibility on the end, so you can see the final equations here. So let's return to the poll in LinkedIn page. The correct answer for this question is tensile, because the internal axial force is tensile for restraint pipe. I suppose that maybe some people just confuse and think that I asked about support load on the anchor and answered the compressive, but the answer 0 is totally incorrect, because the force will not be 0. Now let me tell you how does StarProf pipe stress analysis software deal with Bourdon effect. Firstly, we add the pressure loads on each end of the pipe. So each pipe has the special load on both ends, and it is equal to the pressure multiplied by end cap area of each pipe. So if you will have the model like this and you will analyze it, you will see some deformations, some displacements, and some support loads that is caused by internal pressure. For example, if you have the zero thermal expansion, the operation temperature is the same as ambient temperature, but the displacements will not be zero and support loads will not be zero. And for high pressure piping systems, the support loads and stresses caused by Bourdon effect can be significant. And the second part of this effect is the pipe shortening under the internal pressure. To model this, StarProf automatically shorten all the pipes, and this effect is dissimilar to thermal expansion. So the axial deformation is added to each pipe in the piping system to model this second part of Bourdon effect. Now let's check the pipe stress analysis codes in B31.3 code. This is most progressive code from all ASME B31 codes. It has the recommendation to use the axial force that include the Bourdon effect, that include the end cap forces. In other codes, for example ASME B41.1 and B41.4 and B41H codes, for unrestrained pipes, axial stresses has the special equation that consider the Bourdon effect, but it consider only end cap force for totally unrestrained pipe. But for example, if we have partially restrained pipe, or for example if we have totally restrained pipe, this equation will be incorrect and we should use 0.3 SH multiplied by cross section, this value for totally restrained pipe, and for partially restrained pipe we should use the value 0.3 to 0.5 value multiplied by SH and A. So the results for partially restrained pipes will be incorrect because a different value should be in this place, and this value can be automatically calculated by StarProf software using this method as I described before. So we recommend to analyze the piping system according to the code, and after that enable this option, add the axial force and torsion stress in past StarProf software. And in this case StarProf will calculate the real stresses. It will not use this equation, it will add here the axial force divided by cross-section area, and this axial force will be calculated considering the thermal expansions and pressure forces caused by Bourdon effect, and will be correct for restrained pipes, for partially restrained pipes, and for unrestrained pipes. As you can see here on this slide, the difference between the code equation and the equation that consider the effect of axial force is totally different. Now let's check in which situation we should use the effective axial force and in which situation we should use the true axial force, true internal force in the pipe. Let's start from flange leakage check. In this case we should use effective axial force. Why? Because the equivalent pressure equation already contains the internal pressure of the pipe. So if we will add here the true axial force, we will consider the internal pressure twice. This is incorrect, so we should apply here the effective axial force. For example, for this model it will be 0. What about nozzle and support loads on the pressure vessels, on the steel structures and other? In this case we should use the effective axial force too. Why? How to explain this? For example, imagine that we have the pressure vessel with end cap and we have the pipe with two caps on the both ends. So which force we should apply to the vessel nozzle? When they perform the analysis of the pressure vessel, for example using the finite element method, using nozzle FAM software, for example past nozzle FAM, this software already consider the pressure, the internal pressure in the vessel, and apply it to the end cap of the nozzle, and after that it calculate the allowable loads for this nozzle. So the allowable loads already contain the pressure effect, so you don't need to consider it second time, and you should apply only the force that is caused by thermal expansion, not from pressure. So the using of true axial force is incorrect in this situation. We should use the effective axial force, the support load. Now let's talk about lateral and upheaval buckling. In this case we should use effective axial force too. This is not so obvious, so let me explain. For example, we have two pipes connected with the angle to each other, and we should apply the forces caused by pressure acting on the end caps of each pipe. So the sum of these forces will lead to the force in lateral direction that tends to buckle the pipe. Now let's imagine that we have more angle, more direction changes in this pipe, and now we have free lateral forces that tends to buckle the pipe, that tends to push it in lateral direction. And now let's imagine that we break the pipe to infinite number of sections, and the pressure forces will produce the uniform load that push the pipe in lateral direction. So the pressure load tends to buckle the pipe. Another way how you can imagine it is just imagine that the contents of the pipe, for example the water inside the pipe, is working like the beam, and you compress this beam, and this beam is buckled under the compressive force. So we should use the effective axial force that include the end cap forces, this value, and we should compare this force with the allowable force, for example from earlier equation. This equation can be used only in elastic stage of the pipe, and for plastic stage we should use another equation. The Bourdon effect is very important. A pipe buckling due to internal pressure caused the deep water horizon blowout and resulted in the death of 11 workers and caused a massive ongoing oil spill into the Gulf of Mexico. So this pipe buckled under the internal pressure. There is no thermal expansion of this pipe. It's buckled only due to the effective axial force caused by internal pressure. And this force can be calculated using this equation. Now let me tell you how StarProf pipe stress analysis software deal with true and effective axial forces when it creates the stress analysis reports. The true axial force is used in three tables. The first table is pipe stress. The second table is local buckling of wall, local pipe wall buckling analysis. And the third is the internal forces. There is a special option where you can switch it on or off to see the true or effective internal forces in one table, in this table. The effective axial force is used for support load calculation in this table, for nozzle load calculation in this table, for flange leakage check, here you can see this table, and for internal force calculation if you check the checkbox to see the effective internal forces. And also we have a special procedure in start elements that allows you to perform the buckling analysis, and for above ground pipeline lateral buckling analysis, StarProf use effective axial force. For buried pipeline upheaval buckling analysis, StarProf use effective force too, and also it is used for long radius band analysis. The long radius bands is usually used in the pipelines. This is the band with the great radius, greater than 1000 diameters. This is all that I wanted to explain. Thank you for your attention and see you on the workshop. Thank you.